Hi, good evening. In continuation with the network security chapters, this evening we shall understand Advanced Encryption Standard AES. I am I. Bilal from Ellen Mishra College of Business Management. I shall recommend to view my two previous videos of AES before going into the details of this video, because in this video we are discussing the left portion of the two previous videos. In the previous videos we could not discuss about the inside story of each round. What happens in each round we have to discuss in this video, but we shall proceed with a brief description of the previous two videos so as to make you clear the facts. So AES was proposed by Belgium scientists Dr. Johan Dieman and Dr. Vincent Driesman, which was approved by NIST in November 2001. NIST selected Rindel as the proposed AES algorithm, which we also call Rindel algorithm. So what happens in AES algorithm? We input 128 bits plain text. In contrast to DES algorithm, here the plain text is not divided into two equal halves. Rather, the plain text is represented in 4x4 matrix. So 128-bit plain text is input to the AES algorithm, which after processing produces 128-bit ciphertext. For processing, here in this AES algorithm, mostly we use 128 bits master key. Besides, there are also possibilities of keys with 168 bits, 192 bits, 224 bits and 256 bits. So depending upon the number of bits, the number of rounds of the AES depends. If it is 128 bits, then AES is completed in 10 rounds, and if it is 256 bits, it is completed in 14 rounds. But as 128 bits provide adequate security to the AES, most popular is 128-bit key. So plain text of 128 bit as well as 128 bits of key is input, which after processing produces a 128-bit ciphertext. So AES is symmetric key block cipher algorithm that uses the similar key at both the ends, at the sender end and the same key at the receiver end. Block size remains 128 bits as well as ciphertext also remains 128 bits. Master key is of 128 bits, and as the number of bits is 128 bits, the total number of rounds is taken 10, in which each round uses one separate key or one separate word, because here we represent one key, one sub key as one word, and one word is equal to 32 bits. So there are total 4 rounds. So in total we need 40 sub keys, but before entering into the rounds, a pre-round calculation is performed that also needs one key, that is 4 sub keys. So total number of keys required, total number of sub keys required in AES is 44. So here is the story, brief story of the previous classes. The plain text is input that enters into add round key or pre-round calculation. Here it needs one key that consists of 4 sub keys, 4 words. The master key is of 128 bits, that undergoes expansion to produce 44 keys. So here add round key needs one key, that is 4 sub keys, and actually this add round key is XOR operation of the sub key with the plain text. plain text of is XORed with the sub keys extracted from the master keys. Now after XOR operation, the output enters into first round. This is the first round, and in this first round it undergoes substitute byte process, which is also known as sub byte or S box. S box we have seen in DES algorithm, and the output of this S box or substitute box becomes input to shift rows. Okay, 128-bit inputs to S box or substitute bytes, and after processing it again produces 128-bit output that becomes input to the shift rows process. Here rows are shifted with right circular shift, and the output becomes input to the mix columns processing, mix column function. And the output of mix column function is becomes input to the add round key. Means here again 4 keys are added, 4 sub keys are added, that is the key 2. So here the keys are represented as words W0, W1, W2 and W3. Here W4, W5, W6 and W7 keys are input to add round key. Now the output becomes of this round becomes input to the next round. So it continues for 10 rounds, but in 10th round what happens, the mix column in 10th round mix column process is not done. This process is not done in 10th round, and after the 10th round the output becomes the ciphertext. This we can see here. This is the story of one round. First process is the substitute bytes, then is the shift rows, then the output of shift rows enters into mix columns, and mix columns output enters into add round key, and the output of this add round key becomes input to the next round, round 2, round 3, round 4, round 5 and so on. And after 10th round the output becomes the ciphertext. This is the encryption, and at the decryption end, at the receiver's end, decryption takes place in the reverse order, that we shall see later on. So here is the story of the entire rounds. This is the first round. The output of this round becomes input to next round, and round 2, round 3 and so on. This is 9th round. And what happens in 10th round? This mix column is absent. This is not done in the 10th round. Sub bytes, shift rows, and output of shift rows enters into add round key. And after this the 128-bit text is converted into ciphertext. So here encryption completes, and at the receiver's end what happens, the entire process is reversed. The entire process is reversed. It goes from add round key, then the round 1 becomes the 10th round of encryption process, and round 1 of encryption process becomes the last round. So here again we miss here mix column process, mix column function, and the final output becomes plain text. Each round requires one key in the form of words, 4 words, that is the 4 sub keys. Here the key 1, key 2, key 3 and so on. Here is the 10th key. Okay, W40, W41, W42, W43. So here you can see mix column of round 1, round 2, round 3, mix column of round 9. This remains absent in 10th round. In 10th round mix column rows processing is not done. Now we shall see the details inside the story of each round, details of each round. Now here we can see the representation of different bytes, different bits. The plain text of 128-bit in AES is not divided into two equal halves as it happens in DES. Here the 128 bits are represented in 4 into 4 matrix, 4 into 4 matrix in the form of bytes. Say this is one column, second column, third column, and fourth column. This is input 0, input 1, input 2, input 3, input 4, input 5, 6, 7, and so on. So here one box, one cell contains 1 byte, means 8 bits. Okay, and one column is one word. One word is of 32 bytes. So 8 into 4, 32 bits. So one word is of 32 bits. This is one word, this is second word, this is third word, and fourth word. So this is the representation of input array. This is input array. 128-bit plain text is represented in the form of 4 into 4 matrix, 4 rows and 4 columns. Each cell, each intersection of row and column, that is each cell contains 1 byte. 1 byte means 8 bits. So if we multiply this 8 into 16, we would get 128 bits. So 128 bits are distributed in this 4 into 4 matrix. Now these are state arrays. State arrays are used for storing intermediate results, and this is the final array, output array, final output array that contains the ciphertext. So this is produced after the completion of the 10th round. Now this is the representation of key. Key is of 128 bits like plain text. So key is also represented in 4 into 4 matrix. This is K0, K1, K2, K3, K4, K5, K6, K7, K8, K9, K10, K11, and so on. Again, the intersection of row and column contains, that is called cell, contains 1 byte, that is 8 bits. So 8 bits into the entire cell, you would get 128 bits. 8 bits into 16, this is 16, so we would get 128 bits. So this is again one word, one column is again one word. So this is word 1, word 2, word 3, and word 4. Each column represents one word. So this is one word, this is second word, this is third word, and this is fourth word. Okay. Now from this is the master key representation. From this master key representation, we extract 44 subkeys or 44 words. Okay, from this master key of 128 bits, we extract 44 words or 44 subkeys, W0, W1, W2, W3, and so on up to W22, 42, and W43. W43 because here word starts with W0. So there are 44 subkeys. Now this we can understand well here in this figure. 128-bit plain text is stored in an array of 4 into 4 matrix. So this is 4 into 4 matrix. This is one word, one cell. This is another cell. This is another cell, and one cell contains 1 byte. This is 1 byte. This is second, third, fourth, and so on. So first byte, second byte, third byte, fourth byte, fifth byte, sixth byte, and so on. And this one column is one word. So this is word 1, word 2, word 3, and word 4. Okay, so there are in total 16 cells. Okay, 16 cells means 16 bytes. So 16 bytes into 8 bits equal to 128 bits. So this is representation of 128-bit plain text in an input array. Now these are state arrays. State arrays are also state arrays are used for storing intermediate results. All intermediate results are stored in state array, which is also 4 into 4 matrix. So this is represented as S0, 0, 1, 0. This is 0th row, this is first row, second row, third row, and this is 0th column, first column, second column, third column. So S00 means 0th row, 0th column. S10 means first row, 0th column. Second row, 0th column. S30 means third row, 0th column. This means 0th row, first column. First row, first column. Second row, first column. Third row, first column. So this is intermediate storage in straight array. All intermediate results after input array, all intermediate results are stored in this straight array. Okay, and now this is the output array that stores the final output, final result, and final result is the ciphertext. So this is output 0, output 1, output 2, output 3, output 4, output 5, 6, 7, 8, and so on. It is also in the form of words. One column is one word, another column is another word. So this is word 1, word 2, word 3, word 4. I think it should be clear. Plain text is stored in input array. All the intermediate results are stored in straight array. And the final output that comes after the 10th round is stored in output array, and that is the ciphertext. Now we can see the key representation in more detail here. K0, K1, K2, K3, K4, K5, K6, K7. This is master key. This is the representation of 128-bit master key. And from this master key we extract 44 subkeys or 44 words. One key is equal to one word, and one word is equal to 32-bit. Okay, so this is word 0, word 1, word 2, and up to word 43. In total 44 words. Now after this, the first process of each round is the sub byte. This is the sub byte, okay, or S box. So this is the representation of S box or substitution box. Okay, this is input array. Input array contains 128-bit plain text in the matrix of 4 into 4. Each cell contains 1 byte, that is of 8 bits. Now this 8-bit becomes input to this S box, and after processing it gives 8 bits. We have also seen S box in DES algorithm. In DES algorithm, the input is 6 bits, the output becomes 4 bits. 2 bits are lost. In DES S box, what happens? 4 bits are input, 6 bits are input and 4 bits are output. But in AES, there is no loss or gain of bits. 8-bit input and 8-bit output. 8 bits input and 8 bits output. Okay, this is the input array, right? Each cell contains 8 bits, 1 byte or 8 bits. 8 bits in this, 8 bit in next, 8 bit again in next. So 128 bits are distributed in these cells. So if we take the bits of one cell, right? Say this is the bits of first cell S0, input 1. Now this is 1 byte consisting of 01, 01, 11, 00. Okay, this is the first byte of plain text. Now how do we represent it? The 4 bits are considered to be the row number. First 4 bits are considered to be the row number, and the next 4 bits are considered to be the column number, right? First 4 bits are considered to be row number, and next 4 bits are considered to be the column number. So if we represent it as 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So in this way we can find the final bit 1, 1, 1, 1, and that represents 15. So this is from 0 to 15. This is from 0 to 15. Similarly, column is also from 0 to 15. That means the S box is of 16 into 16 column. Size of the S box is 16 into 16. Okay, this gives us the row number, first 4 bit, next 4 bit gives us the column number. Fine. The total size of the S box is 16 into 16, means 256 cells are there in S box. Okay, now how do we process? Here we can say this is S box consisting of 16 rows and 16 columns. Okay, here we can see 0 to 15, that is the F in hex system. So 0 to 15 means 16 rows and 16 columns. So the S box contains 16 rows and 16 columns. Okay, these are columns and these are rows. So S box is a representation of 16 by 16 cells matrix. Now this is S00, S10, S20, S30 and so on. So here what happens, if we take any particular bit, any particular box or cell, there would be 8 bits in this box. So if we take the example of this box, there would be 8 bits in this box, and from those 8 bits we take the row number from first 4 bits and we extract column number from the next 4 bits. Okay, this decimal number gives us the row number, and this number when converted into decimal system gives us column number. Okay, 0101 would be converted to decimal number and that would be the row number. Again 1100 would be represented as column number, that would give us the column number. So from this row number, column number, we go into the S box, and particular row number and particular column number intersection is the destination. Means we have to, this is the cell, we have to get the value from this cell, and getting this value from S box, it is converted again into the binary numbers and it is stored in corresponding cell, corresponding box. So the value was taken from S11, and after getting the value and converting it into binary number, this is again stored in S11, but this is another state matrix. So if it is S matrix, it is S dash matrix. Okay, S dash 11. So if the value, we take the value from here and then go to this box, this S box, and then we get the value from this S box after converting it into binary number, that result would be stored in this one. Again, if we take the bits from here and from these bits we get the row number and column number, then we from the S box we collect the value from the given row number and column number, and from that particular cell we take the value, convert it into binary number, and then we store it in S-33. So S is input, S dash is output, S matrix is input, S dash matrix is output. We can understand it here with an example. This is the S box, 0th column, first column, second column, third column, fourth column, fifth column, and so on. This is the 0th row, first row, second row, third row, and so on. Now how do we pick the value from this S box? We can understand here. See here, suppose we get a value from particular cell. Suppose we get the value from here, this S00, and the value stored in S00, just imagine, is the value 00010000, 8 bits, right? First 4 bit would give us the row number and next 4 bit would give us column number. So decimal representation of this 0001 is 1 and decimal representation of this 000 is 0. Okay, so here first row and 0th column, this gives us first row and 0th column. So now with this we enter into this S box, first row and 0th column. So this is 0th row, this is first column, first row, this is first row, and 0th column. The intersection is here, 74. Now we take this 74 from this S box, and then 74 is converted into binary number. We can see here 74 is converted into this binary number 01001010. Now this value is stored in S dash matrix here, because we had taken the value from this S00. Now this converted 74 would be stored in S dash 00. Okay. Similarly, the value from this 10 would be taken out. First 4 bit would give us the row number. Next 4 bits would give us column number, and it would be converted into decimal number. That would be the row number and column number, and then we enter into this S box. The corresponding value is taken and it is converted into binary number, and that binary number would be stored in S10. Similarly, S20 value from S20 would be taken and converted into row number, column number, and would be done in the similar way. So this is the story of S box. I think it should be clear. Now the output, this is the output, say this is the output. This output becomes input to next process, that is shift row process. Better I would say it in the block diagram. Here you see this was the S box sub byte, and the output of this sub byte would become input to shift rows. Okay, this is the second process of one round. Now here what happens? The bits undergo right circular shift. And how many bits would be shifted? It depends upon the row number. If it is row 0, no bits would be shifted. If it is row 1, 1 bit would be shifted. If it is row 2, 2 bits would be shifted. If it is row 3, then 3 bits would be shifted. And the result would be stored in another state array, which is called shift array. So now we can see here. Say this is the output from S box. Okay, this is the output from S box. Now this is S00, S01, S02, S03, and this is the 0th row. No bit would be shifted. So here we find the similar result as it is S00, S01, S02, S03. Now this is row 1. In row 1 we have to shift 1 bit. This bit would be shifted to last location, and the second bit would become first bit, third bit would become second bit, fourth bit would become third bit. Okay, first bit would become last bit, and second bit would become first bit, third bit would become second bit, and so on. So in this way S11 would come to the last position. This would be taken by S. Oh, this is incorrect actually. Here we can see, yes, it is correct. A10 is here, A10. Now this place is taken by A11, and then A12, A13, and the first bit becomes the last bit, A10. Okay, so in second row 2 bits would be shifted, means A20 would come here, A21 would come here, A22 would take this place, and A23 would take this place. A22 would take this place, A23 would take this place, A20 here, and A21 here. In third row 3 bits would be shifted, means A33 would take this place. So A33 has come here, A30 would come here, A331 would come here, A32 here. Okay, this is incorrect matrix. Now we can see it here more clearly. What happens in 0th row? No shifting. In 0th row, no shifting of bits. S00, S01, S02, S03, S00, S01, S02, S03. No change in position. but in first row, one bit would be shifted. So this first bit comes here, this position is taken by second bit, and the second position is taken by third bit, and third position is taken by fourth bit. So S10 comes here, S10. Now this position is taken by S11. This shifts to here, S11, then S12, S13, and in second row 2 bits would be shifted. So this bit would come here, and the last bit would come here. First bit would go here, and second bit would take the last position. So here we can see S20 is here, S21 takes the last position, S22 takes the first position, and S23 comes to second position. S22, S23, S20, and S21. And in third row, 3 bits would be shifted. So the last bit becomes the first bit. S33 becomes the first bit. Okay. And the second position is taken by S3.030, then S31 and S32. This is the output of shift row transformation, shift row process. Okay, this output becomes input to next process, mix column process, mix column function, which is the third process of one round. We can see here, mix column. First we have taken S box, then shift rows, and then now mix column. Now we shall see the mix column. This is the output of shift row. It becomes input to mix column page, mixed column process. Here in mixed column transformation, what happens? Matrix multiplication takes place. Here there is predefined matrix. This is the predefined matrix consisting of values 2, 1, 1, 3, 3, 2, 1, 1, 1, 3, 2, 1, 1, 1, 3, 2. This is a predefined matrix. Okay. Now this is the input matrix, input array that has come from the shift row transformation process. Okay. Now here matrix multiplication would take place, means this is the matrix of 4, 4, and we have to multiply with one word of this output of shift row process. So this will be 4, 1 matrix, 4 rows and 1 column. Okay, and the rule says here the column number of one matrix must be equal to the row number of the next column, next matrix. Column number of one matrix must be equal to row number of another matrix. So here column is 4, and here row is also 4. So matrix multiplication would take place. Now by multiplying these two matrices, this predefined matrix and one word from this matrix, would be placed here. So S00, S10, S20, S30 would be placed here. Okay, one word, see here, one word, and this one column matrix would be multiplied by this predefined matrix. Is it clear? This is predefined matrix, and in this space would be filled by this one column of input, S00, S10, S20, and S30. This would come here, and now multiplication would take place. This would result in again 4 into 1 matrix. Okay, one column matrix, 4 rows and 1 column. Now this would be stored here. Okay, S-00, S-10, S-20, S-30. Clear? Now this place would be filled by second word, second column, S01, S11, S21, S31. Now after multiplication it would again produce 4 into 1 matrix. Okay, Now this result would be stored in this state array as second column. So S dash 01, S dash 11, S dash 21, S dash 31, right? And similarly, this third column would take this place, multiplication would take place, and the resultant would be stored as third matrix of this result state array. And then fourth column would come here, and the result would be stored here. So this is S matrix and this is S dash matrix. This is the output of mixed column transformation. This is the output of mixed column transformation that becomes input to the next add round process. So here we can see this column comes to this place, okay, this place, and the result is stored here, and this result is stored in S dash matrix. Similarly, the second column would come here, third column would come here, fourth column would come here. Now, what happens in add round key? In add round key, each word is XORed with one word of the key. Okay, each word means one column. Each column would be XORed with one column of 44 keys. Okay, so here is 44 keys, no, not 4. Key is represented also as 4 into 4 matrix. This is one word of key, this is second word of key, this is third word of key, this is fourth word of key. Okay, so this column would be XORed with this first word, right? K1, K2, K3, K4. Similarly, the second column would be XORed with second word, K5, K6, K7, K8. In the same way, third column would be XORed with this third word, K9, K10, K11, K12. Okay, and the fourth word of this result, this matrix, would be XORed with fourth word of the key, K13, K14, K15, K16, and so on. So if we take it from W0, it would be, final would be W15, and so on. So this is the result. XOR this column with this word with this word, and the result is stored here. Similarly, the second word XOR with this second word and stored here. Third word would be stored here. Fourth word would be stored here. So this is the output of add round key transformation. Okay, this is the output of first round. This is the output of first round. Now it enters into second round. It enters into second round here, third round, fourth round, and fifth round. What would happen? There won't be any mixed column process. In the 10th round, there won't be any mixed column process, and the output of this add round key would become the ciphertext. And at the receiver's end, the ciphertext would be decrypted in the reverse order, giving us the final plain text. So this is all about AES. We have learnt in this session the inside story of each row. Each round contains 4 processes: S box or sub byte or substitution bytes. Second is shift row. Third is mixed column. Fourth is add round key. So this is the representation of input array, that is in plain text stored in input array. This is the intermediate results storage in state arrays, and this array is for storing the final output after the completion of 10th round. That gives us the ciphertext. So and this is the representation of key in the form of words from W0 to W43. Each round needs one key consisting of 4 words or 4 subkeys. So in total we should have 44 words or 44 subkeys. So this is S box. In S box, 8 bits are input, 8 bits are output. Then comes shift row. In shift row, right circular shift takes place. Then is the mixed column transformation, where the output of shift row transformation is multiplied with the predefined matrix. So each row, each column, each word multiplies with this predefined matrix, and the resultant is stored here. And this resultant enters into the next phase, add round key transformation, where the output of mixed column is XORed with the key. One word of this state matrix, this result is XORed with W0, the second with W1, and so on. Now this is the final output that enters into second round, third round, fourth, fifth, sixth, seventh, eighth, ninth, and in 10th round there is no mixed column process, and after the 10th round the output like this becomes the ciphertext. So that's all about the AES. Thank you.